So in this particular video, we'll be focusing on what differential privacy is and how we're gonna add that particular noise to a differentially private recommendation system. So what is a recommendation system? Well, a recommendation system is a subclass of information filtering system that helps to predict the rating or preference a user would give to an item. They're primarily used in commercial applications. Netflix and Amazon could be given as two major platforms which use the recommendation systems in order to improve the user experience. It is also used by Spotify for recommending songs and by Google to recommend personalized ads. There are three types of recommendation systems. Number one is context-based system, in which, let's say, Netflix will recommend you a movie based on its description, its name, its genre, the year it was released in, etc. Collaborative based systems are the systems in which Netflix would recommend you a movie based upon how other users have rated a particular film, and based on how you've rated the films you've seen, it will correlate the data and give you the preference. And at the end is hybrid based system, which is a combination of context and collaborative based recommendation systems. So for this particular example, we're going to be focusing on collaborative based systems. So collaborative filtering has many forms, but many common systems can be reduced to two steps. The first step is to look for users who share the same rating pattern with the active users for whom the prediction is for. The second step is to use the ratings from the like-minded users found in the previous step to calculate a prediction for the active users. This falls under the category of user-based collaborative filtering. A specific application of this is the user-based nearest neighbor algorithm. Collaborative-based systems. Collaborative-based recommendation systems are the most susceptible to a privacy-based attack. Well, this is because instead of one of the users, it will particularly aggregate all the data from all users. On the flip side, however, this system has huge potential gains in regard to enhancing user experience. So let's see what are the privacy risks associated with collaborative systems. We're going to be focusing on two of them. So the first one is when Narandan and Shmatikov, two well-known researchers, demonstrated a powerful and practical de-anonymization attack which linked records in a Netflix price dataset with public IMDb profiles. They took their attack one step further, considering a scenario where an individual maintained two different profiles, say a professional blog and a pseudonymous page on a social network, which had occasional discussions of disjoint sets of movies, which were rated on Netflix. Then it was possible that they could be linked to the same Netflix price row and thus they will be linked to each other. Whether the movie ratings attributed to this individual were embarrassing, revealing, or at all remarkable was irrelevant. It was the fact that the two personas which were meant to be linked that can be perceived as deeply invasive of its privacy, and it was disturbing as well. The other example we're going to look is with a recommendation system based on user-user similarities. The attacker can in fact create a fictitious profile or many profiles resembling an individual based on attacker's partial knowledge and induce the recommendation system to faithfully report all items highly rated by the individual. So these are big problems, and how can we tackle these risks? So we think that having a differentially private system, we help to deter these particular attacks and create more advanced systems in which we can provide better recommendation based data set. So a differentially private recommendation system is what we're going to be focusing on from now on for the rest of the slides. So we thought to twist this problem a bit and offer information of how a differentially private system should work. So we will be focusing on an implementation of differentially private system. For this particular example, we have used the movie lens database, which is available online. Our objective is to find out whether the differentially private systems would also give us as good results as a normal recommender system. Differentially private recommendation systems. To develop a system like this, we're going to be following 5 steps. Number one is to pre-process the dataset. 2, add noise to the ratings. 3, to develop a correlation matrix. 4, to generate similar movies based on the type of movies the user likes. And at the very end, we're going to deliver the results. So this might seem too complex or too fast for people to understand. So what we're going to do now is we're going to help you visualize what is going to happen. So first we're going to pre-process the data set. First we're going to drop the ratings which are not available, and what we're going to do is we're also going to be keeping only the data of the users who have rated more than 10 films. We hope that this will help us in performing data cleansing, which will remove the data which won't contribute much to the results in a vital manner. So this is how our data set would look without the noise. This is a pandas data frame which has been generated using two files, ratings.csv and users.csv. As you can see, after performing pre-processing and cleaning the data, we now have 610 users and 2,269 movies and a lot of zeros. But I assure you, this won't affect our final results. So now let's focus on how should we add the noise. To add the noise, as we talked previously, we will be adding a randomized Laplace distribution to our ratings. Based on the current data set, we selected an epsilon value, which is the privacy budget of 2 and a sensitivity of 1. So this is how our data set would look after the noise. As you can see, the zeros have been replaced by a random value in each of the cells. And now we can say that the data is differentially private. To offer a better example of visualization, let's just see quickly. This entire row was of zeros, right, for user 1. After making the data set differentially private, the row becomes a bit noisier, as you could say, right? So we can say that now the data set is differentially private. So let's move on to see what is a correlation matrix. So what is correlation? Correlation is from the world of statistics, and it's key to help us find out whether the relationship between the two variables and how it can be useful in data analysis, modeling, etc. So correlation can be of three types. It can be positive when both variables change in the same direction. It can be neutral when no relationship between the change of variables exists, and negative correlation when variables change in opposite directions. Now, for this example, as we needed covariance and standardization, we used Pearson correlation, which can be summarized to strength of the linear relationship between the two data samples, in this case, movies. It can be calculated as the covariance of the two variables divided by the product of the standard deviation of each data sample. And it is also the normalization of the covariance between the two variables to give an interpretable score. So how would a covariation matrix look? Well, this is how it looks now. So as you can see, let's say 500 days of summer and 500 days of summer, the max value of this particular cell is 1, which is the maximum correlation possible. So as these movies are the same, its value of correlation is 1. Now let's see how we're going to use this particular matrix to get the recommendations. So how our system works is a user in this case will submit the movie and its ratings. For this example, let's say the user is a big fan of animation movies and he submitted two movies, Toy Story 3 and Ratatouille. He rated both the movies 4 stars. So what we're gonna do is for each movie we will iterate over the movies and we will get its respective column from the correlation matrix. We will then take the rating submitted by the user and subtract it by its average rating, which is 2.5, which was mentioned in the research paper we followed, and multiply it to the correlation matrix value we received. Then we're going to sort the column and return the films and its ratings. This particular step is performed until we iterate all the movies, and at the end all the data is collected per movie appended in a data frame, and it looks something like this. Now, as you remember, there were two movies we discussed, right? So this is how it will look at the very end, but it doesn't look right, right? You cannot make understand what this actually is. So let's change things up a bit. The results right now don't make sense right now. So what we're gonna do is we're gonna sum all the values and sort them as our user based on their rating seems to like animation or Disney movies. We expect them to see in it our recommendations. So let's see if that is the case. So step 5 was to deliver the results. Let's see if the results have delivered. So if you look at that, the top results are Toy Story 3 and Ratatouille, which were the two movies the user really liked. So after that, you can see these two movies have resulted in a higher correlation value. But if you look down, you will see more Disney or animation films like Up, Incredibles, Finding Nemo, Cars, Wall-E, Monsters Inc. So let's compare these results with a normal recommendation system to see if that gave us a better result or this gives us a better result. So the side-by-side comparison of the differentially private system and the normal system, we see that if you see a differentially private system result in The Incredibles is highly recommended in a differentially private system, as in a normal system we get recommendation of Sherlock Holmes, which is a bit difficult to understand. It's not that great. So as you can see, there's not much of a difference, but the recommendations in differentially private system seem to be better than a normal system. So let's look at another example. So now we have a user who likes action adventure movies. So let's say in this particular example, when we have a side-by-side comparison, we expect the user to be recommended action adventure movies. So when you see a recommendation system in this case, which is differentially private, you see the user has been recommended Amazing Spider-Man, Mission Impossible, and Fast and the Furious, which he already rated. And then we get X-Men, Hellboy, King Kong, and other installments of Mission Impossible, which is pretty good. In this particular case of a normal system, the user gets recommended Over the Hedge. Over the Hedge is a 2006 animation film, but the user doesn't like animation film. As we can see clearly, he rated Toy Story 3 2 stars, so we didn't expect this to be too high. And this particular recommendation system also doesn't give recommendation of other Mission Impossible films, which our system did. So we can say that based upon our findings, we can say that a differentially private recommendation system provided us with very good recommendations while also preserving user privacy. In some queries, we receive better results as compared to the results from a normal collaborative recommendation system. We believe that using a differentially recommendation system could prevent attacks such as de-anonymization attacks in the future. The future scope can be defined as you can maybe fiddle around with the system more. You can see if it gives you better results by using a better privacy budget or sensitivity value. We also think like you can experiment by adding different types of noise, maybe exponential noise, see if that works. Our implementation was inspired from the research paper Differentially Private Recommendation Systems written by Ilya Mironov and Frank McSherry. If you have other recommendation system research paper, we urge you to try and develop a system based on different research papers, see what kind of system would be better in the future. These are our references. We would like to thank them for providing us with the information and data through which we learned a lot, and it really helped us in the implementation of our differentially private recommendation system. So thank you guys for watching. This is Raaghavv Devgon on behalf of Megan Skrobacz. We are part of CS6760 of Northeastern University. We thank you for watching our video on differentially private recommendation systems. We hope you found it useful, and maybe you will develop your own recommendation systems in the future, which are differentially private. So thank you, and maybe now it's time to go binge watch some movies. Thank you very much.